Assalamualaikum warahmatullahi wabarakatuh, and welcome to another session of EPO 640 electric drive. Okay, so for today we will be discussing on our first topic. Okay, so our first topic will be on electric drive. Okay, electric drive concept, method, design tools. Okay, so this will be part one. So for this time, we will be looking into the drive system overview, okay, some system considerations, and also drive application. So you all know what is a drive system. So it's commonly known as a VSD, variable speed drive, also known as a adjustable speed drive, or simply electronic drives. And what does it do? It provides a controlled variable speed drive, either a rotational or a linear drive. And also it provides controlled torque. So you have um, two items that you measure, okay, in a basic electronic drive. That is the speed and also the torque. So how does VSD looks like? Okay, in blocks in system. So first you have your electric motor. Then you have your mechanical load, okay, the application, the hoist, or conveyor, or whatever mechanical load that is needed. So the electric motor is connected, okay, to the power electronic converters that provides the power to the electric motor. So depending on the type of motor that you have, okay, either it's a DC or AC drive. So the power source will be supplied by the power electronic converters that will be also connected to a fixed power source. So power source can be AC or DC. So the function of the power electronic converter is convert, okay, to a suitable power source that is required by the electric motor. Okay. So all the outputs of the power electronic converters, the output of the motor, the output of the mechanical load, okay, uh, will be sensed by a sensor. Okay, so you will sense the position, the speed, the motor current. So all this information, all these signals will be sent to the control algorithm, or the microprocessors. So the microprocessors will dictate, okay, based on our input speed or our input torque. Okay, so it will give the right switching signal to the power electronic converters. Okay. And motor drives, so you have some example here. So you have the induction motor, you have the switch reluctant motors, okay, permanent magnet motors, okay. Also, you have a linear motor that is being driven by so here you have your commercial inverters, and also power electronics. And the measurement, okay, it's been measured by okay, current. If it's measured by either a shunt or resistor, current shunt, or current transformer, or also a transducer. Okay, and speed is measured by tacho generators. So tacho generator is a DC generator which gives a voltage proportional to the speed, and also it can be measured by digital encoders. Okay, so digital encoders is a slotted disk with a light source, so giving up a pulse stream which has a frequency proportional to the speed. Okay. So application of electronic drives. So you have for low power, okay. So low power, you can see for small electronic products such as your electric toothbrush, your DC drive, your watches, okay, or your household tools, your electric drills, okay. And then you have your kilowatt to megawatt ranges, okay. So you see some bigger application for manufacturing industries such as for lift, hoist, cranes, okay, fans, pumps, machine tools, and also you can see it on the electric vehicles, in Tesla or Nissan Leaf. And then you have the large application, okay, 10 megawatt upwards. So usually for trains and large wind turbines, ships, okay. And for comparison, you have your power station. Okay, power station generators are usually 2 to 6 gigawatt. And next, we will look into the design, okay, of an electric drive. So the design of the electronic drive is to suit the mechanical specification. So sometimes you must know, not sometimes, you must know what the mechanical system specification, okay, that is to decide what demands will be made to the power supply. Okay, so the mechanical system is seen as a torque that must be applied to the shaft by the motor coupling. Okay, and it is very important to match the drive to the load. Okay, so we have to match, for example, you have to match the torque and the speed capabilities. So some application they need high torque but low speed. Okay, some application needs high torque and high speed, or some application needs low torque, high speed. So you have to know the torque and speed capabilities. Okay, and usually to define the relationship between the drive to the load, we use the 4-quadrant torque speed curve. So here you can see the 4-quadrant torque speed plane. Okay, so in some textbooks, okay, you have your y-axis in torque, okay, x-axis in speed, or vice versa. Sometimes it's explained, okay, y-axis is speed, okay, x-axis is torque, okay, or sometimes they don't use torque, they use current. Current instead of torque, they use instead of current, they use current instead of torque. Okay, and speed also sometimes they use the armature voltage, with the positive and negative. So different textbook they have different explanation on how this 4-quadrant torque speed plane. Okay, so hopefully in the future you don't get confused. Okay, so for the purpose of explaining the 4-quadrant, okay, so we will be using okay, different types of 4-quadrant, okay, torque speed plane. But all in all, you only have you have either motoring or generating, okay, in your 4-quadrant torque speed plane. Okay, so for motoring, basically the load torque opposes the direction of the motion, okay, and the energy transferred from supply to the load. So the torque developed by the motor is in direction of the motion. Okay, whereas in generating, so the load torque is in the direction of the motion. Okay, the energy transferred is from the load to the supply. So the torque developed by the motor opposes the direction of motion. Okay, so in a 4-quadrant torque speed plane, so you have motoring, you have forward motoring and reverse motoring, and for generating also you have forward generating and reverse generating. Okay, so the mechanical system, okay, mechanical system comprises common elements associated with the drive motor and the load system and the specific load torque. Okay, so it's the symbol is TL, okay, to be driven. So common elements include friction. So friction is the torque to drive the mechanical system without doing additional mechanical work. Okay, so you have frictions in the surface, friction, and in the bearings. Also, okay, so that will be the equation. Okay, and windage torque, which move the air, okay, surrounding the moving parts of the drive. Okay, so torque W. Okay, that will be the equation. And also you have the acceleration. So the torque developed to overcome the mechanical inertia and the change of its speed. Okay, so you have TA, okay, with that equation, okay, to counter the moment of inertia. So you have the equation of TE. Okay, so TE torque developed equals to torque load. okay, the mechanical load, torque load, plus, okay, torque friction, torque windage, and also torque acceleration. Okay, so you have your torque balance equation. And this is example of a steady state characteristic, okay, of the load. Okay, so some of the motors that is suitable for fan speed, centrifugal pump, fan speed. So you need the torque to the speed ratio, okay, is linear, okay, but until it reaches the rated torque and rated speed. Whereas for loads that has high inertia, okay, so for example, for machine tools, traction, for constant power load, so you have this initial torque that is needed to pick up the motor, and then when it reaches a certain speed or torque, so that will be when it achieves the rated speed. Okay. So we have defined the load as having a torque speed characteristic, and the mechanism which drives the load must be capable of matching the load's torque speed characteristic, okay, to achieve stable system operation. Okay. So therefore, the motor and the electronic drive system is also defined in terms of torque speed characteristic. So the drive must be rated to provide extra torque for acceleration or short-term overload if required. Okay. So so let's discuss on the operating range of a motor. Okay. Okay. So torque. Okay, torque developed is usually a function of a current, and you have your maximum torque is proportional to the rated current, which is determined by the cable size. Okay, and there is usually a maximum voltage which we can apply to the motor, and usually it's related to the supply voltage and its flux level, winding structure, insulation, and so on. So there is usually an induced back EMF in the motor that is proportional to the speed and flux level. So high speed operation is related to the maximum motor voltage and flux level. And the absolute maximum speed is determined by the mechanical constructions, okay, such as you have frictions in bearings, in couplings, and so on. So, for example, in a motor drive, so if you can see here, your torque, your torque with will have a rated torque. Rated torque will reach until the base speed. So base speed is within the maximum torque that you can apply. But if you want to increase your speed further, okay, so it can also be done, okay, within the maximum limit, max speed. Okay, so this will be, just as we discussed before, will be the mechanical maximum speed. Okay, and this can be achieved with field weakening. So let's say usually to operate a motor at its rated flux density, okay, so if it's higher, it will cause magnetic saturation and extra flux related losses in the motor core. If it's low, means that you are not maximizing your torque to M ratio. Okay, and at rated speed or at rated voltage, or we say that at base speed, okay, so the rated voltage is K1. K is the what you call it, the pemala, what you call it, constant. So the constant, okay, constant, machine constant, okay, times base speed, okay, times the rated flux. Okay. So it can potentially go faster by reducing the flux while applying rated voltage. Okay. So for example, if we reduce the flux to 90% of the rated value, the speed will increase by 1.11 okay, times the base speed. Okay. So it's always a compromise to achieve max torque value available reduces, okay, the 90% of the rated torques, rated flux. So you are sacrificing torque to achieve higher speed. And other important things that you look for design features, you have your the characteristic during steady state, okay. You have the dynamics, okay, the supply, either AC or DC, okay, the environment, okay, high ingress protection. So usually for DC motor, you have low, okay, IP rated, okay, not suitable for hazardous environment and so on. So in conclusion, the electronic drive usually comprises of a motor, power converter, sensors, and controllers. And we need to understand both the load requirements and the system environment requirements when selecting and designing the drive. Okay. So what we use is the torque speed analysis. Okay. So you can please refer to the textbook, okay, for further reading on this topic. So this will be an example, okay, example of a mechanical specification, okay. So you can try to do this within your free time, okay. Okay, so then we look into the application of variable speed drive, okay. So rotating, okay, mechanical system. So you have your torque, your force, force, torque. Okay, so torque is force times the radius. Okay, and then you have your angular velocity is tangential velocity, and power is torque times the angular velocity. So for also to deliver the power to the mechanical mechanical load. So sometimes you will employ gearbox. So gearbox, the concept is you have different numbers of teeth. It means that the cog rotates at a different speed. Okay, so it's a ratio. So gear ratio normally given in terms of output speed or the input speed. Okay, so n equals to omega 2 out of omega 1. Okay, that is if the gearbox is 100% efficient. So if it's 100% efficient, you have your power in equals to power out. So so speed 1, speed 1 times torque 1 equals to speed 1, speed 2 times torque 2. Okay, so then you can say that torque out is equal to torque 1 out of the ratio. But unfortunately, gearbox are not 100% efficient. Okay, so the gearbox absorbs power irrespective of which side it is applying power. Okay, so note that gear ratio 1 to n means that speed out, speed out is n times faster than speed 1 or speed in. Okay, so you can look into the figures here. And okay, so another example that you can look into, in a paper roll machine. So you can also do this in your later on, by yourself. So another example, also you can go through this during your as a revision. So thank you, and we will continue with part 2 of our session. Okay, thank you. We will continue on part two in our session.